Okay, we'll today look at a very important topic in linear algebra called the SVD or singular value composition. Okay. Earlier, maybe 2 modules back, we talked about similarity transformation, right? What is this? What is similarity transformation of a matrix? Yes, say the similarity transformation is this process of moving from one matrix to another, where both the matrices represent the same geometric operation, right? And for similarity transformation, both A and B have to be what? Square matrices. Input space, output space are same, Rn. Okay, and okay, they represent the same geometric operations, but then what is the difference between them? Yes, they represent the same geometric operation in different bases. So how do I algebraically go between A and B? How are A and B related algebraically? Okay, if you write it like this, then you have to tell me which of the two represents the geometric operation A or B in the standard basis and which one represents in the X basis. This is in the standard basis. Why? Okay. Are you saying that because you remember, or can you figure this out from here? Can you logically argue why this has to be in the standard basis and this has to be in the X basis? When we say X basis, we are talking about the basis X1, X2, Xn, where these are columns of X, the matrix X. Can you logically argue why this is? Okay, if you're not sure, you should be able to do this. It's good to remember, but you should so that you can immediately recall. But you should also be able to logically argue why this is. This is correct. So this is in the standard basis. This is in the X basis. Okay. And we also saw that if you choose, or in most matrices, except for maybe some barring a few exceptions, if A represents a geometric transformation operation in the standard basis, it is possible for us to obtain a very simple algebraic representation for A if we choose the basis correctly. And when we say a very simple algebraic representation for a matrix, the simplest possible matrix is non-trivial matrix is your diagonal matrix, right? So we can find a very simple form for the geometric operation represented by A. If A is a non-diagonal matrix, we can find a diagonal matrix if we choose the basis appropriately. And what basis is that? In what basis of A, or in what basis of Rn does A look like a diagonal matrix? Yes, it's in the eigenbasis. Okay, now let's say V is the eigenvector basis. Is it V inverse V or V inverse? Yeah, okay. Right? So we can do this for most matrices that are diagonalizable. Any matrix that can be written like this is, we say A is diagonalizable. Right? Otherwise you say it's not diagonalizable. Okay, but let's say we had a weird situation. Okay, so here, if you want to work in the standard basis and do this geometric operation, you use A. If you want to work in the V basis, if you're working in the V basis, then you use lambda. What if I wanted to do this? Now here both my, for example, if y equals ax in the standard basis, then I know xv, which is the representation of x in the v basis, multiplied by lambda will give me y represented in the v basis. This I know, right? Where I've chosen to work in the v basis for my input vectors and the output vectors. What if I had a weird obsession and I said, I don't want to use the same basis for the input and the same basis for the output. I want two different bases. Okay, my inputs come from, let's say, some basis v, and I want my outputs to be in some basis u. You understand the question? Here, both my inputs and the outputs, I was happy to represent them in the v basis. But let's say we have a strange problem where the inputs come from, I want to work with vectors that come from the v basis, but I want this matrix, the equivalent matrix of A, to produce the output, but not in the v basis, but in the u basis. And I will call that matrix A u v. Inputs come from the v basis, outputs come in the things that come out of this matrix will be the equivalent representation in the u basis. How is this related to A, which is all in the standard basis? This is equivalent to writing standard basis, standard basis. Both inputs and outputs are in the standard basis. This one, on the other hand, is simply AVV. Output in the standard basis, input in the standard basis. How would these two be related? I'm not going to write this. It's understood that if we don't write anything, it's all in the standard basis. You understand the question? Yeah. How would A and UV be related? Yeah, both of them represent geometrically the same operation. It's just that my inputs all come from V basis, and I want the output of this. When I do that matrix multiplication, I want the output to directly give me the output, directly give me the vector in the U basis. Tell me the exact expression. Tell me the relationship between A and AUV, or the other way around, or this, whichever you are comfortable with to start with. If you know one, you can figure out the other. Yes.
And you're getting that output as what is V.
Yes.
And you want it in the U, then we will add U.
Here?
U, why is the U plus?
Sorry, U? Sorry, okay. Okay. Your thought process is correct. Okay. Input comes in this.
So the output.
So the input comes in here. You're saying I multiply by AV, is it? Okay. Maybe I should clarify. Here I was simply talking about diagonalization. Okay. Let's say now I should have said that we are moving on to a different problem now. V need not be the eigenvector basis. V is some basis. So the representation of A in the V basis, if both my input and output bases were V, is not lambda. It's AV, let's say. Do you see what I mean? Okay. If that is the case, then what would be the relationship between these two? In fact, let's say this. You have A, this is in the standard basis. You have AV, right? Representation of the same geometric operation in the V basis. When I only write one subscript, that means both the input and the output are all in the V basis. How is this related to A? And AU is if the representation of A in the U basis, input and output are all in the U basis. Okay. How is this related to A? Let's first figure this out and then we'll go to this. representation of A in V here. Are you sure? Yeah. Yeah, this one? Right, that's all. Okay. This we figured out, right? If I want to only work in the V basis, then I use this matrix instead of A. If I only want to work in the U basis, then I use this matrix instead of A. But that's not what I want. I want my inputs to come from the U basis, and I want this matrix to directly give me the representation of the vector in the U basis. Then how are A and UV related? You can tell me whichever one you are comfortable with. Input, output. Yeah, you have it? Which one? This one or this one? This one? Oh, A UV equals? Okay. U inverse. Why is it U inverse? Yes. Okay. If you look at A, right, what basis does A take inputs in? Just A. No, just the matrix A. The matrix A takes inputs in the standard basis, produces outputs in the standard basis. So whatever you multiply on this side, what comes out here is all in the standard basis. Yeah. AV. So there will be V here. U U this one or hey, what does the inverse operation do of a matrix? What is an interpretation of A inverse or U inverse? What does this do? Sorry? That is one interpretation. What is the other interpretation? Change of what? Okay. What does it take input in? What does it produce? What basis, from what basis do stuff go in here, and when what basis do stuff come out? What is this? Standard basis. Are you sure? Or it's not the other way around? I'm just asking you. I'm not saying it's wrong. I want to confirm that you know for sure. Huh? Yes. No, I can have identity matrix in uh, in any arbitrary basis. This is correct, but I'm just making sure. I want to know if you're sure about this. Okay, so it takes stuff in the standard basis, gives stuff in the U basis. Okay, now can you then figure out this? This is wrong. Well, see, this matrix expects things to come in the U basis on this side, and it expects things, and it will give out stuff in the U basis. Okay. Now, if I use the matrix A, right, A only takes stuff in the standard basis. So I cannot stick XB here. If I stick XB here, you will get a number, but it will be wrong. It will not be it will not be the number corresponding to the geometric operation that A does. Okay. I get this, right? I have XV because all my inputs are in the V basis. But A only works with the standard basis. So I have to convert XV from the V basis to the standard basis. Conversion from the V basis to the standard basis is done by V. Okay, if I multiply this, X is from the V basis. Once I multiply by V, I get stuff in the standard basis. Then now this is okay. A expects stuff in the standard basis. It will do the geometric operation and give me the output in the standard basis. But what I want is in the U basis. To convert from the standard basis to the U basis, then I simply do U inverse. Okay. If both U and V were the same, this would, for example, if it is all in the V basis, right, then this will be V inverse. If this is all in the U basis, then this will be U. Here. So these are special cases of this. What did you not understand? Because we covered this in inverses also, right? We covered this in inverse, and we discussed this in eigen decomposition as well. What is not clear? Here, there is no XV here. The matrix is this. See, you have A is all in the standard basis. Things go in the standard basis, things come out in the standard basis. If I have a vector and I want to apply this geometric transformation, I simply take X multiplied by A, and then I get the corresponding geometrically transformed vector and its representation in the standard basis. Okay. If I was working with AV, the corresponding operation would be XV, and I'd get, if I was working with U in the U basis, then I'd get XU, and I'd get the corresponding representation in the U basis. Okay, but AUV is strange. AUV will take stuff from the V basis, but the output it will produce will be Y. Okay. So if this takes input in the V basis and produces output in the U basis, and A is all I have, then to use A, I need to make sure whatever I multiply from this side is in the standard basis. But what I have is in the V basis. To convert from the V to the standard basis, I need this. This is standard basis. This is V basis. What comes out is in the standard basis, but what I want is in the U basis, and all I have to do is U inverse. This is in the U basis. So this whole matrix now is okay. What is taken as input is from the V basis, what comes out is in the U basis. Internally, there is this process of converting to the standard basis and then to the U basis. Okay. Okay. See, earlier when we did similarity transformation, since we were working with the same basis, right? Or let me put it this way, we were only dealing with matrices that map from Rn to Rn. So we could work with the same basis for both the input and the output. So you could have something like this. Okay. If you're still dealing with matrices A and B that map Rn to Rn, and you want to work with two different bases for the input and the output, you could do something like this. But if you have rectangular matrices, right? Let's say A and B are two rectangular matrices, n cross m. We cannot define a similarity, for example, let's say A represents a geometric operation from Rm to Rn, okay? And let's say B represents the same, or for example, let's say we ask the equivalent question. Is there another matrix B, n cross m matrix B, which represents the same geometric operation as A, but in different bases? Okay? The problem there is, what basis? Because your input space and output space are not the same. There is no one single basis you can work with, right? Because the basis that you choose in, let's say you choose a basis in Rm, but that basis cannot be used in Rn because the spaces are different, right? So if you are talking about two matrices which represent the same geometric operation from Rm to Rn, and you're talking about their representations in a different basis, you have to specify two different bases. The basis that you're using for the input space Rm and the basis that you're using for the output space Rn, right? Which is equivalent to this problem. Okay, so this transformation here is a more general transformation where if you happen to be working with two different bases, for the one for the input space, one for the output space, right? Which is by choice in n cross n matrix, because both the input space and the output space are from Rn. But if you're working with rectangular bases, you will have two different bases. You will never have the same basis for the input vectors and the output vectors, right? So in that case, you can still ask, are there matrices which represent the same geometric operation, but in a different basis for the input and the output, right? Those matrices can be represented like this, right? If V is a basis for Rm and U is a basis for Rn, okay, then, and A is in the standard basis, then A, B, this will be U, B inverse. Okay. Okay. In this case, both A and B represent the same geometric operation. A represents everything in the standard basis, but the standard bases are different. You should note it represents a geometric operation where the inputs come from are represented in the standard basis in Rm. The output are all represented in the standard basis in Rn. Okay, whereas B represents the same geometric operation in the V basis for Rm and the U basis for Rn. Okay, and A and B are called equivalent matrices. I don't know if it's called an equivalent transformation, but you can check that later. But these are called equivalent matrices because they separate. They have the same flavor as this. In fact, this is a more general version of that. The similarity transformation is a special case of this, where you're working with the same. If U is V, right? That means this has to be an M cross M matrix, right? Because V is a basis for Rm. If this was U inverse, then that would mean A and B are n cross n matrices. Okay, so it turns out that for rectangular matrices also, you can have an infinite number of matrices representing the same geometric operation, but in different bases. Okay, except that now your input basis and the output basis are two different bases, not the same. Okay. In the case of square matrices, right, we could ask, okay, is there a matrix, is there a diagonal matrix that is similar to A in some arbitrary basis? Okay, for for most matrices which are diagonalizable, the answer is yes. If you choose the eigenvector basis, there is a diagonal matrix that is similar to A, right? Here in the V basis, A and lambda are similar. This is when you're dealing with n cross n. Well, you could try and ask the same thing here, right? Okay. If I have a rectangular matrix, I'm saying this transformation will allow you to find other matrices that represent the same geometric operation in different bases. Then you could ask, are there special bases u and v such that if I choose u and v appropriately, this B matrix is as simple as possible, has a diagonal form, okay, and that's essentially your SVD. And in fact, the SVD is another matrix decomposition or another form of matrix decomposition, and it is arguably or maybe or is one of the most general decompositions because it exists for all matrices. There are no conditions. Any matrix has an SVD. Okay. Whereas if you look at LU, what type of matrices have LU decomposition? Square matrices. What type of matrices have QR decomposition, where Q is orthogonal and R is upper triangular? What is the condition on A for QR decomposition? For Q is orthogonal, but R is upper triangular. It has to have full column rank. Okay. What about eigenvalue decomposition? Square? No. Need not be full. Need not be full rank. And in fact, all full rank matrices might not have. Yes, it has a full set of eigenvectors. Then you're guaranteed eigenvalue decomposition. SVD on the other hand turns out exists all the time. Okay, and let's say A is a n cross m matrix. Then the SVD of A is simply written like this. Transpose. Okay. And there is another or interesting property. When we did eigenvalue decomposition, right, where we were diagonalizing a matrix A, for most matrices you could find an eigenvector basis such that you get this, right? The eigenvector basis need not have been orthonormal. Right? It's just an arbitrary basis. That's why we write V inverse. But when A is symmetric, right, then we could write it like this. Right? When A is symmetric, you could choose an eigenvector basis that was an orthonormal basis, right, and you had a representation like this. Right? The eigenvalue decomposition is a lot simpler than taking the inverse. Right? Another great thing about the singular value decomposition is for any matrix A, there is an orthonormal basis for the input space and an orthonormal basis for the output space, in which A looks like a diagonal matrix. Okay. So here you remember the expression for the equivalent transformation AU B V inverse, right? The V inverse was because it was not an orthonormal basis. It was just an arbitrary basis. But the SVD says for any matrix A, there exists an orthonormal basis for the input space, which is V, and an orthonormal basis for the output space, which is U. And the equivalent representation of A in these two bases has a diagonal form. We'll explain each of these terms first. So V, okay. So this is n cross m. So this is n cross n, no, m cross n. M cross n. This is n cross n. What shape will this be? It will be n cross m. Well, it has to be, right? If this is equivalent to this, it has to be an n cross m matrix. Okay, but now you should ask me something, or you should be worried. I'm saying this is a diagonal matrix, but I've written a rectangular matrix. Okay. So what we mean by diagonal is that it's block diagonal, or it's like this. So sigma will in general have a form like this: D 0 0 0. This is n. This is m. Okay, and this D on the other hand will actually be a diagonal matrix. Sigma 1, sigma 2, sigma r. We'll write r for now, and this is 0. This is 0. Okay, so this is a R cross R matrix, but it's a diagonal matrix. Okay, and then the other 0 matrices have the corresponding dimension. This is m minus r. This will be n minus r. This will be n minus r, m minus r. Okay, so when we say sigma is a diagonal matrix, this is what we mean. Okay, all the off diagonal entries are 0, and you will have non-zero entries in whatever partial diagonal that you have. For example, if it's a tall matrix, then the diagonal is like this. If it's a fat matrix, then the diagonal is like this. Okay. So that's what we mean by sigma being a diagonal matrix, even though it's a rectangular matrix. Okay. Not just that, right? These sigmas that you have, they are all positive. So sigma r is greater than 0. Okay. And the convention is you order these sigmas such that the largest value is sigma 1, the next value is sigma 2, and so on and so forth. Sigma 1 is always greater than or equal to sigma 2. That's by convention. We just choose to write it like this. Okay, and these sigma i's are called the singular values of the matrix. These are equivalent to the eigenvalues of an eigen decomposable matrix of A. Okay, so that's sigma. Okay, V is an m cross m matrix, and V transpose V is V transpose is I m. V is an orthogonal matrix. That means the columns of V form an orthonormal basis for Rm. Okay, and U is n cross n, and U transpose U transpose is I n. That means U is orthogonal. The columns of U are form an orthonormal basis for Rn. Okay, and because here this diagonal matrix D is R cross R and has R non-zero diagonal elements. In this case, the rank of A, or if you're wondering what this R is simply the rank of A. Okay, so now if you have a matrix A that is an n cross m matrix with rank R, then the singular value decomposition of this matrix A is this. Right? Sigma would be this is sigma. This is sigma. This is your V, this is your U. Okay, and the most important or an important thing to note is your singular values are always positive numbers. They cannot be negative. Okay, and if the rank is R, there will be R non-zero singular values. Okay, and U and V are orthonormal basis for Rm and Rn, and that's, I mean, now you could ask, okay, what are these? How do we find out U, V, and sigma? Okay. Okay. If A can be written like this, right? Tell me what is A transpose A, and tell me what is A transpose. First of all, are these two symmetric matrices? Yes or no? How will you find out if it's a symmetric matrix? Yeah? Yes. So tell me whether it's symmetric or not. Yeah? Is it symmetric? How will you find out if it's symmetric or not? Can you verify? What is A? If this is, for example, if this is one full matrix B, B transpose is equal to B. Can you verify and tell me if B transpose is B? No? You're not sure? Okay. You have to check if this is symmetric. You have to verify if this is equal to. How will you verify this? No? Okay. Well, there is nothing to do here. There is something that can be done here. You can take the transpose inside. What will happen if you take the transpose inside? You transpose. Whole transpose of this. Okay. So you get this, right? So both, in fact, you can verify this is also symmetric. If it's symmetric, what can we say about eigenvalue decomposition? Does eigenvalue decomposition exist? It exists, always exists if it's a symmetric matrix, okay? What more? What can we say about the eigenvectors and the eigenvalues if it's a symmetric matrix? Yes. Eigenvectors? Orthonormal, okay. Are these two positive definite or positive semi-definite matrices? Okay, so I mean we did the problem yesterday, so these will be positive semi-definite. Okay, they could be positive definite, but positive semi-definite for sure. If that is the case, what can we say about the eigenvalues? Yes, so they can only be positive or zero. They cannot have negative, right? Okay, so now since we know the singular value decomposition of A, tell me what is A transpose A and AA transpose in terms of the singular value decomposition. So do you have it? Okay, what does A transpose say? No, tell me the simplified version. Okay, then this will be U sigma V transpose or transpose U sigma V transpose. Remove this. So if we take the transpose inside, this will be V transpose transpose, which is V sigma transpose, okay, U transpose. I'll write it like this, and then U sigma V transpose. Okay. Yeah. Okay. This will disappear because it's an orthogonal matrix. So what you end up having is this V sigma transpose sigma V transpose. We can't write sigma square yet, okay, because this is not a square matrix. This is a rectangular matrix. There is no square for a rectangular matrix. You can think about why that is. You cannot square a rectangular matrix, okay. But we know what sigma looks like. Sigma looks like this. Sigma is D, which is a square matrix, square diagonal matrix, 0, 0, 0. What will be the shape of A? Sigma transpose sigma? M cross M, right? Okay. And you can verify later on that this will be M cross M and it will be of this form. This I can square. D is a diagonal matrix or square diagonal matrix. This I can square. And the zeros here this will be of size M minus R, 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 M minus R. Okay. I'm going to write it as sigma square. No, I won't write it. It will only create confusion. No. Okay. It's this. That means this can be written as V D square 0, 0, 0 V transpose. Okay. Or which is equivalent to saying this is simply V sigma 1 square, sigma 2 square, sigma R square, and then a bunch of zeros. V transpose. Okay. This is a symmetric matrix. And we've written it as V some matrix V transpose. And this is a diagonal matrix. Okay. Eigenvalue decomposition is unique for a matrix. Okay. V inverse, because V is an orthogonal matrix, V inverse is V transpose. This is a diagonal matrix. That means this is the eigenvalue decomposition of A transpose A. Okay. Because this is the diagonal matrix. Okay. And that simply means that now we know what V is. V is simply the set of eigenvectors, or the set of the columns of V are the set of eigenvectors for this matrix A transpose A. Okay. So V is eigenvectors of A transpose A. Okay. So V is not some magic matrix. It's simply the eigenvectors of A transpose A. Okay. Now similarly, tell me what is A transpose. In fact, I want you to tell me in this format. Yes, yeah. So it will be U. What will be the size of this? No. N cross N. So it will again be sigma 1 square, sigma 2 sigma R square, 0, 0, U transpose. And now we know what U is. U is simply the eigenvectors A transpose. So we've kind of gotten a handle on what U and V are. What about these sigmas? Well, in fact, the sigmas are simply the eigenvalues of A transpose A or A transpose. And sigma I square are eigenvalues of A transpose A or A transpose. Okay. And notice these are squares. Sigma are real numbers, so these will be positive. So these will be positive semi-definite because you've got R non-zero values and then 0 eigenvalues. Similarly here. Okay. So that's essentially what these three terms are. U and V are eigenvectors of A transpose and A transpose A respectively. And your sigmas are simply the square root of the eigenvectors of A transpose A or A transpose, or the square root of the non-zero eigenvalues of A transpose A or A transpose. And if the matrix A has rank R, there will be R singular values because A transpose A and A transpose will have R non-zero eigenvalues. Okay. So that's one level of understanding this. In fact, the singular value transformation or decomposition gives you even more. So we write it like this. Transpose. It turns out that, let's say this is of rank R, right? How many columns do we have for U and how many rows do we have for V? N columns, M rows, right? So the columns would be U1, U2, UR, and then from there UN. Okay. What about the rows of V transpose? They will be V1 transpose, V2 transpose, VR transpose, VM transpose. Note this is V transpose, not V. That's why I've not put the tilde. Okay. And then here you have sigma 1, sigma R, 0, 0, 0. Okay. When you write it like this, right, it turns out this section and this section and the remaining section, this and this. If you take those vectors, right, those will be a basis for a R-dimensional space in Rn. Okay. The remaining will be a basis for, or orthonormal basis for, n minus R dimensional space in Rn. Similarly here, the vectors v1, v2, vr will form an orthonormal basis for a R dimensional subspace in Rm, and the remaining will form a orthonormal basis for m minus R dimensional subspace in Rm. Okay. And it turns out that this is simply an orthonormal basis for the column space of A. Okay. And these form an orthonormal basis for the row space of A. Okay. You can tell me what this might be then. What is this a basis for? Or what do you think this will be a basis for? Yes. So this will be, turns out this is an orthonormal basis for the null space of A, and this simply is an orthonormal basis for left null space. Okay. So if you look at this, right, if I take any vector x, okay, x belonging to Rn or M, sorry. Okay, if I multiply these two, I'll get another column vector, and the column vector will simply be V1 transpose x, V2 transpose x, so on and so forth. If I multiply this, right, with the sigma matrix, okay, the first R columns have non-zero numbers. The other remaining columns are all 0. That means whatever you have here, right, essentially scales 0 columns. That means these essentially get nullified out, right? That means the component of x in the null space gets nullified out because of these 0 columns. Okay? And then if you look at these two, right, the 0 rows of this matrix will correspond to the last n minus r columns of U, which are basically from the left null space. That means you have no contribution from these columns. So what you will get has only components from the first R columns. Okay, it's probably not easy to see it initially, but if you think about it a little bit, you'll get the hang of it. Okay, so the singular value decomposition kind of connects back to our 4 fundamental subspaces as well. In fact, it gives you orthonormal basis for the 4 fundamental subspaces of A. I'm going to quickly say a couple of things and then we're done. Okay. See, when we talked about the eigenvalue decomposition, right? Eigenvalue so there are 2 different ways we can view a matrix, right? One is simply view it as data, just a bunch of numbers arranged in a rectangular form, or as a transformation, right? Something that takes vectors, operates on them, and then produces another vector, right? It turns out that the eigenvalue decomposition is a very useful decomposition if you view A as a transformation. Okay? We'll see why that is later on when we discuss applications of eigenvalue decomposition. The SVD, on the other hand, turns out to be a very useful tool when you're simply looking at the interpretation for your matrix is that it's a bunch of data. For example, if you have a tabular data, right, with columns and rows, maybe some measurements, and these are patients, right? You have tabular data. You could interpret this as a transformation, but I don't know what that would mean. Okay, but as a tabular data, this makes perfect sense, right? Because each ijth element tells me the jth measurement for the ith patient, right? So if you have data like this, it turns out the singular value decomposition tells you something about the structure in this data. Okay? And that's one of the major uses of SVD. And in fact, if you're talking about data like this, for example, if you have an image can be viewed as a matrix, okay, where each pixel is simply a number. Okay? It turns out you can use SVD to find structure in your image. And what I mean by structure is SVD, of course, tells you exactly the rank of A, the rank of your matrix A, which is a data matrix for us. Okay? Not just that, it turns out the SVD can give us approximations of the data of the matrix A, and these are approximations of a lower rank. Lower rank. See what that means. Instead of just writing it like this, right? If you expand this out, you can verify this later on. I won't say why this is true. If you expand that out, right, what you will end up having is this. You will have sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose, and you will have R such outer products any A of rank R can be written like this. Okay. Now, let's say you have some data like this, okay, and you do the singular value decomposition and you compute the singular value sigma 1, sigma 2, sigma R. Right? Let's say you find sigma 1 is around 1000, whereas sigma R, the last singular value, is around 1. Okay. This would mean that the contribution of this very last term, right, is very small, right, compared to the contribution of the first term, right. So, one thing I can say is, okay, if I want to store A, I would have to store R singular values and then R columns UR and R columns VR, V1 to VR, right. But if my first singular value is 1000, the last singular value is 1, maybe maybe this is not contributing that much to my data. So I can afford to lose this without losing too much structure in my data, right. So you could say, okay, I'm going to simply get rid of this. If you get rid of this, what you have is a different matrix, not A, right. I'm going to call that A R minus 1. Okay. If I get rid of the last term, right, what is the new matrix A R minus 1? Rank is minus 1. A was of rank R, you had R outer products like this. If I get rid of the last term, right, then I have rank R minus 1. So now if I have the SVD and I find that you have singular values like this, if I simply knock off the last component of this last outer product, then I get an R minus 1 approximation of a matrix whose rank is R. Right? If I find that the last L singular values are a very small value compared to the other singular values, then if I simply knock those L elements out, L singular values out, then I will get, so from A, let's say I drop the last L singular values, okay, then I will get a R minus L rank approximation of A. Okay. So the structure that we are talking about, when I said SVD finds structure in your data, it simply finds out the rank of the matrix, and in fact it finds out more. It tells you or when you write the SVD like this, depending on the values of your sigmas, it allows you to find approximations of your matrix A of lower ranks. Lower rank means you have to store lesser numbers and maybe you can see better structure. Okay, if there are too many, if the rank is very large, then there are too many independent directions in which my data can be distributed. But if my rank is say 1, then I know my data is only distributed along a line. If the rank is 2, then I know my data is distributed in a plane, 2-dimensional plane, and so on and so forth. Right? So SVD essentially allows you to find a simpler representation of your data depending on what the value of your these singular values are. Okay? So in fact, it turns out SVD gives you the best possible approximations, best possible low rank approximations. Okay. And what we mean by that is, let's say I take the full matrix A, okay, and I find a rank K approximation of A. A was of rank, so this was of rank R, this is of rank K. K is less than R. Right? I find a rank K approximation of A, right? And I ask, what is the best possible rank K approximation of my matrix A? Okay. It turns out the SVD gives you that. The best possible rank K approximation of A is you simply only keep the first K singular values and you remove the rest, you get rid of the rest of them. Okay? So that's essentially a major application of SVD, to find approximations of data which are equivalent, which maps to finding simpler representations of your tabular data. Okay, all right. So that's all I wanted to say about SVD. You can go back and review the slides to again recall all of this. That completes almost all theory except for least squares. Okay,